the technology we're using to fulfill and to facilitate our 5 and 6 gigahertz high performance coexistence Wi-Fi filters. Just so some more descriptions, I won't read this. Obviously, you can read this yourself. Basically, we are a leader in SAW and ultra-BAW, as I mentioned, with filters up to and including some UWB 8 gigahertz filters as well, which we won't talk about today. And what this webinar will get into is why you need BAW filters for Wi-Fi, or you certainly need high performance filters for Wi-Fi to realize the performance that our colleagues at Qualcomm, for example, are put forth with the platforms, very demanding channel widths and so on. And I won't go through this again, but basically our ultra-BAW filters offer low insertion loss while offering high nearby selectivity, which is obviously the key for these systems, coexistence of between 5 and 6 and so on. I'll get into a little more detail as we move forward. So, what does a typical Wi-Fi system look like? These are just some examples. Of course, there's dual band. I'm starting here with the tri-band. Tri-band, many designs today, if not most designs today in the Wi-Fi systems, access point routers are going to tri-band. So tri-band Wi-Fi 6E and Wi-Fi 7, very prominent in the design world today. And you'll see the first Wi-Fi 7 systems introduced here in a couple months based on the Qualcomm platform. So we're really excited about that whole Wi-Fi 7. It seems to have been pulled in a number of months. The market really needs and wants this high performance Wi-Fi 7 MIMO, MLO features of Wi-Fi 7, for example. So again, this is just a typical block diagram, and with our filters noted, which right now they're just numbers to you, but we'll get into that and tell you what they mean in a bit. And next, so tri-band, here's quad band, typical quad band block diagram. So as you can see, many components from the radio to the transceiver, from antenna to filters to front-end modules as well. And finally, what's becoming totally clear now, the more bands, the better. So pentaband is next, and there's already a number of these in design at our key customers in the world, for example. So this talk is about filtering, not about Wi-Fi systems, but I just wanted to give a quick overview of that. So why do you need filtering, and why do you need ultra good filtering? You need it because of coexistence. So on the left side, in the box to the left, we're showing let's say the traffic at 2.4 gigahertz. The band 40, band 41, band 7 has been around for as long as LTE has been around. And now with 5G, the reuse of those bands, let's call it N7 and 41 and 40, are still there, and actually a bit more demanding in terms of emissions. So therefore, if you're operating your 2.4 gigahertz Wi-Fi, in some cases even Bluetooth, you need a really strong filter to protect, let's say, the Wi-Fi signal, and vice versa. But in particular, the high power LTE signal or 5G signal, you want to protect your Wi-Fi. The filters that we offer in our portfolio do that, and I'll go through that real quickly in a moment. On the right side, we're talking about the coexistence between a couple different coexistence, mainly the coexistence at the 5G frequencies, let's call it the higher bands, the sub-6 gigahertz bands, and 77, 79, which N79, as you can see from the picture, is basically right on top of your low side of your 5 gigahertz Wi-Fi signal. Our filters are designed to attenuate those and offer very good performance right next to it. Let's give it that way. Let's put it that way. Right adjacent to it. And on the right side, you have to worry about your 5 gigahertz spectrum, whether it be Uni 1 to Uni 3 or Uni 1 to Uni 4, coexisting with your 6 gigahertz, which is off to the right, which I'll show you in a moment. So this was our focus and remains our focus. And we're just showing a little bit here the differences between what a SAW and a BAW filter can do versus some typical LC type of filters or multi-layer filters, whatever you want to call them. They are certainly good filters, but when you're talking about coexistence, you need the acoustic filters. This is our favorite slide here at Qualcomm. It shows the complete portfolio on one page, which us marketing guys like to do. To the left, you can see we're starting at the 2.4 gigahertz spectrum, and the components that we have there. So as I mentioned earlier, the global channel 1 to channel 13. Let's say, for example, down below, global coverage products, B7520 as a perfect example. And of course, band edge mainly for the US, channel 1 to channel 11. We have a couple different offerings there. The B7539 on top there in the darker red, excuse me, is what we called our Ultra SAW product. To the right, you could see the Uni 1 through Uni 8 spectrum, 5 gigahertz and 6 gigahertz, and the portfolio that we offer there, very full and still expanding. But we now offer filters for the Uni 1 to Uni 3 to the 4, and the sub, let's call it the high-low bands, the low-high bands and 5 gigahertz, for example. And now, as I mentioned, that penta-band, which is why I did that, you're going to break the 6 gigahertz into 2 as well. So you'll have a low band 6 gigahertz, so Uni 5, and a high band Uni 7 to Uni 8. It just depends on the designer, on what you're trying to do, how you go about that. We also have the full band filter for HVS, or high band simultaneous type of architecture, down below the B8382, and below that, just to give an idea of some diplexers that we also have in our portfolio, which I won't get into too much detail today. And here's the boring slide, but we have to show. We're obligated to show these. No, not really, but basically what I want to show here is our Wi-Fi filter packages. You can see from 0907 up to 1814. These are the smallest packages in the industry for not only 2.4 gigahertz, in particular for 0907 as an example, but for this 5 and 6 gigahertz filters. So our 5 gigahertz filters are in the 1.4 by 1.1, or as we call it, 1411, and our 6 gigahertz filters are in 1814. So these are considerably smaller than let's say other technologies, and also smaller than our competitors. So why does that mean anything? Mean something? It means something because as the increase in MIMO content, so from 2 by 2 to 4 by 4, and going deeper than that, higher than that, that's more filters. Because of the coexistence, you need the coexistence filters. So the front end looks very crowded. You need to reduce the size of the filters to get them all in the space without getting them too close to each other, with the right grounding and so on. Just briefly, just to give you an idea of the performance of these filters, you can see to the left, this is our Uni 1 to 3 and Uni 1 to 4 full band filters. And you can see the sharp rejection on the left to attenuate the N79, for example. And of course, the sharp attenuation on the right, let's say steep slopes on the right, in order to provide the coexistence with the 6 gigahertz. And this is our 6 gigahertz filters, or Uni 5 to Uni 8. And the key there, of course, is a very sharp curve on the left side, very sharp slope on the left side, needing to reject the Uni 1 to Uni 3 with, let's say, up to 50 dB of coexistence or rejection of the Uni 3 band. On the right side, so far, not much to worry about, so we let that roll off a lot slower so far. You never know what's going to happen in the 7 gigahertz area, but thank you. Right now, it's not a concern, so we're able to focus on insertion loss and very high rejection on the low side of the 6 gigahertz. And just wanted to show this to give you an idea of how they work together. It's called multiband. So the Uni 1 to Uni 3 plus the Uni 5 to Uni 8, as you can see, very good coexistence. They live together very nicely. Then moving forward, just to give you an idea here, these are what I was talking about with what we'll need for certainly for the quad band and for the pentaband, where we're breaking up the low band and the high band of 5 gigahertz, for example, which is actually best shown on, better off showing up this one. This is a much better way. So Uni 1 to 2A plus the Uni 2C to 3 plus the Uni 5 to Uni 8. So 5 gig low, let's call it, 5 gig high with full band 6 gigahertz. And you can see all needing to coexist with each other. And we continue to design new generations, new versions to improve the rejection, which is the key to the entire system. The better the rejection, it goes back all the way to the antenna and provides the necessary isolation from 5 to 6 gigahertz. Meeting compliance, obviously FCC compliance and so on, as well as your own system compliance. And just another look at it. This is with, again, Uni 1 to Uni 3 with the Uni 5 and Uni 7 to 8. Just different variations of what the systems will look like down the road. So we offer, working with customers, of course, data sheets. We offer the evaluation boards, we call EVBs. This way you can basically test them yourself on your bench and get the same results. These are typical results, of course, at 25 degrees, and of course our data sheets will provide the full over temperature and so on, minimums, maximums, and so on. We offer support, from board layout to the end of the system design and vice versa. Board layout for 5 and 6 gigahertz filters is very, very critical, very, very important. Different than what we've all been used to in the past, working with 2.4 gigahertz or gigahertz types of frequencies. Placements of dias and things like that are so important. And we offer, I don't want to call it a service, but we offer personal assistance there, free of charge. Here's a look at our full band or HBS filter used in mobile phones in particular, and other IoT types of devices, where you're not breaking the 5 and the 6 gigahertz. It's one continuous, one radio, and you just antenna to filter and just filter out the N79, for example, in this case. Very interesting, going to Wi-Fi 7. HBS becomes really important, and then on the bottom you can see I define HBS for you. It's a multi-link technology from Qualcomm. It's a feature that leverages the 2 Wi-Fi radios simultaneously in order to achieve the more streams, in this case 4 streams, of high band connectivity in the 5 and 6 gigahertz frequencies. So the way we do that is, say, the platform is designed that way, of course. We do have a set of front-end modules, which I'm not talking about today. That would be a different webinar. But we do have a set of front-end modules specific for this application. And more to the right, what I looked to in yellow, the QXF 2077 is a 5/6 gigahertz diplexer. QXF 2077 takes your signal 5/6 gigahertz and diplexer. So you could use your one, basically takes your signal 5 to 7 very interesting part that, again, depends on the application. It's not for necessarily access point or router, but more for, let's call it fixed wireless, or let's call it quote unquote IoT application. And there's a short description of this component. As you can see, bottom left is the most important thing. Uni 1 to Uni 3, Uni 5 to Uni 8 diplexer. So 2 signals in and 1 signal out. And these are, let's say, 2 filters in one component. And that concludes, let's say, the presentation part. Any questions? We have plenty of time for questions and answers, so I think you can type them in, and we can go through them and answer them one by one, as long as we have time.
Yeah,
Katie will monitor that.
Yeah, Cliff, perfect. Yeah, exactly. For all the attendees, you can enter them into the Q&A window, click submit, and then that question will pop up here in our queue. We will get to as many questions as we can. We do have a couple in here already, Cliff, so I'm going to read out the first one here, and we can give the attendees some time to ask a few more if they'd like. So our first one here, Cliff, what are the benefits of ultraband filters versus ceramic filters?
Ultra-BAW.
Yes.
That's okay. Ultra-BAW and ultra-high, that's okay. Yeah, so the main advantage, of course, would be high selectivity, low insertion loss in a small package. Those 3 attributes make that, you know, I don't want to toot our own horn here, but makes that the best filter for the application.
All right, so great. Thank you so much for that answer. All right, so we have another one here. This person is asking, is there any support for custom frequency bands?
Yeah, that's a great question. Yeah, that's pretty much what has put, let's say, RF360 on the map for the past 25, 30 years. We are very open to doing custom frequencies / custom bandwidths, custom whatever. Not so much custom pinouts or anything. Packages, we try to stay standard as much as we can. But custom frequencies, as long as I have to give my marketing verbiage here and say, as long as the business case is the right business case, with the right volumes and right return on investment, then sure, we're totally open to that. Absolutely.
All right, Cliff, thank you so much for that answer. Just a note to our attendees before we go to the next question. Along the bottom of your webinar console, there are some widgets. And then just below the Q&A window, you can take a peek at an item that we have in the resource list that is available for download. So feel free to grab that anytime before the webinar ends today. And any questions that you have, enter them into the Q&A window and click submit. All right, Cliff. So a couple people are asking about the presentation. So we are not going to be making the presentation available for download today, but we do have that great resource listed in our resource list for everybody. So feel free to grab that item, but we will not be sending the presentation out today. All right, so our next content question, Cliff. What is the smallest and largest package size of Wi-Fi 6E and 7 filters?
Okay, that's a good question. That was one, I went briefly over that in the presentation. That's okay. Well, for 2.4 gigahertz, the smallest is 0907, so 0.9 by 0.7 millimeters. And the largest package would be for our 6 gigahertz parts, which is 1.8 by 1.4, or as we call it, 1814. That's where, and then some other sizes in between. But we have a 5 gigahertz, which was very impressive, actually, in a 1.1 by 0.09, so 1109 package for 5 gigahertz ultra-BAW. By far the smallest 5 gigahertz filter in the market, on the market.
Okay. All right, perfect. Thank you so much, Cliff. So we have a couple more questions in here. We'll move into those, and then anybody has any new questions, feel free to enter those at any time. So Cliff, the next person here is asking, how much component footprint area is saved using Qualcomm ultra-BAW and ultra-SAW filters compared to DR or ceramic RF filtering?
Okay, so let's just take the DR first. And DR, I guess you mean dielectric resonator filters. It's a ceramic technology. Those are quite large. Typically, depending on, I mentioned we have from 1109 to 1814, so you have to say, depending on which one of those, but easily 70, 75, maybe even 80% space savings. So
all right, thank you so much for that answer.
And I guess if you multiply that, I was just going to say, if you multiply that by a 4x4 MIMO, I don't know, it's like 500 or 600% space savings or something. I didn't do the math, but so it's 8 filters times 70% space savings, so it's 560% aggregate. Go ahead. I'm sorry, Katie.
No, yeah. Thank you so much, Cliff, for that answer. So we do have a couple more questions in here. We're going to just go to the next one here. What is the typical counterband rejection and insertion losses for Qualcomm's 5 and 6 gigahertz filters?
Okay, yeah, it's a good question. Typical, I kind of breezed through those plots, but sorry about that. But the answer to that is pretty simple. The typical value for a rejection is, let's say, 50 dB. And by typical, that's at 25 degrees and all those typical things on a typical day, right? In a typical day in New York City, something like that. And the typical insertion loss is, 2.5 dB in the passband.
All right, great. Thank you so much. All right, we have a new one that just came in. So Cliff, this person is asking, any info on power handling capability?
That's a great question. Yes, we do. That's not a very good answer. Yeah, so typically we rate our ultra BAW filters at, it's a typical kind of a parameter. It's 28 dBm, and that's at 50. And our condition of test, let's say, is 55 degrees C with a 70% duty cycle. So anything different than those parameters, we could simulate that for you. We could calculate that for you and tell you what the maximum power would be. Let's say if it's 100% duty cycle, or if it's 20% duty cycle, or if it's in 25 degrees instead of 55 degrees. So I said a lot there, but so yeah, so data sheet wise, it's 28 dBm at those conditions that I mentioned.
Okay, great. Thank you so much, Cliff. So just a reminder to our attendees, we do have some items in the resource widget, and then we have a survey, which is also located along the bottom of the attendee console. That survey's just got some questions about how we did today. Your feedback is always important to us. So at the end of the webinar, or if you'd like to click on the survey now, you can start to fill that out. We would appreciate it. All right, Cliff, we've got a couple left in here. This person is asking, do you expect to be able to support the newer UNNI-4 5 gigahertz channel and the full low-end 6 gigahertz UNNI-5 anytime soon? And I apologize if I'm pronouncing anything in there incorrectly.
No, that's okay. It's Uni, yeah, but
yep.
That's okay. Uni 4. So we do support the Uni 4, Uni 1 to Uni 4, or the Uni 2C to 4, for example, with that, let's call it 5 gigahertz filter. And of course, we support the coexistence with our 6 gigahertz filter to Uni 3. Right now, we're still, because of the technology of filtering, not only acoustic filtering, but all kinds of filtering, you need a certain, it's getting into physics now, but you need a certain transition in order to provide the rejection slopes. You don't quite have enough. It's only that's between Uni 4, the high side of Uni 4 and the low side of Uni 6 is only 50 or 60 megahertz, and that is just not enough transition. So we're working on some new technologies to offer that. But for Uni 1 to Uni 3 with Uni 6, yes, that's what the question before about what is a typical rejection, and that is typically 50 dB. So from Uni 3 to Uni 4, that's still a challenge. So we're working on that.
All right, great. Thank you so much for that answer, Cliff. So we are going to give everybody a few more minutes to ask any questions that they may have. And it looks like we have a couple more that popped in here. So Cliff, this person is asking, is the power limit driven by thermal issues or by non-linearity?
Thermal. It's environment. Let's say it that way. Thermal and the duty, the environment of the actual application. So duty cycle. So temperature is key. High temperature. Low temperature is not so bad. High temperature and high duty cycle is not a friend to the filter. Put it that way. But it's not a linear issue, no. Linearity issue, no.
Okay, great. Thank you so much for that answer. All right, another person here is asking, can you please comment on whether ultra-BAW resonators use an air cavity or if they are a solidity-mounted configuration?
Wow. No, it's not air cavity. I'm not sure what's meant by solidity mounted. It's piezo technology. It's bulk acoustic wave piezo technology. So it's a chip mounted on a substrate with a package. It's not cavity filter at all. I think that answers the question.
All right, great. Thank you so much. And then for anyone that's asking a question, we will always be able to reach out to you following today's webinar. So if there's any follow-up that you have, feel free to enter that in, and we can always get back to you as well. All right, Cliff, so another one here. This person is asking, how would one begin to engage on the possibility of a custom design?
Yeah, that's pretty simple. We have sales reps, so we would, reach out to you with our sales rep, and then we have Richardson, who also can get involved. So we have a form, let's call it a Word form, where it provides you an opportunity to put in the parameters that you need, that you want, let's say. So the frequency, center frequency, the bandwidth, the insertion loss, power, everything. Or we can just go email back and forth, with Richardson and our reps in the loop and work it that way. So pretty simple, no barriers, no dumb questions, no dumb requests. We take them all on, and if we can do them, and like I said before, the business case is there, we will engage, absolutely. And we'll go back and forth. So that'll be the first thing we do. We go over the spec, and then we may negotiate. Well, we can't quite do that bandwidth, or we can't quite hit that insertion loss with that rejection. So we'll say, can you live with this? Can you live with that? And finally, we meet in the middle, or not. And maybe you do need a different technology. Maybe you need a cavity filter, depending on what you're trying to do in terms of power, for example. Cavity filters are almost unlimited in power handling versus acoustic filters. So yeah, it's a simple process, to be quite honest.
All right, Cliff, thank you so much for that answer. So we've got a couple attendee questions left. We're going to give everybody another couple seconds to write in any last-minute questions, and then we've got one more in here that we can go to. So I'll give everybody another second or two to type in any last-minute questions that they might have. And then, Cliff, we do have this last question left in here, so we'll start with this one, and if anybody types in any new ones, we can always jump over there. But this last one that we have in here, what is the typical lead time?
Yeah, typical lead time has been, and will be 12 weeks. And while, I have to say, during the times of logistics issues in the world, semiconductors and all, we remained steady at 12 weeks, even 10 to 12 weeks.
All right, Cliff, thank you so much for that last answer. As I mentioned, I'll give everybody another couple seconds just in case there's any last-minute questions that somebody would like to ask. While we're waiting to see if any last-minute questions come in, I'll just go over the items that we have available for you one more time. We do have that PDF listed in our resource list. And along the bottom of the webinar console, there's a couple other widgets, one of them being a survey. Feel free to fill that out and let us know how we did today. All right, Cliff, it does look like we got one more question popping in here, so let's grab this one. Is external,
yes, that's a good question.
Yep. Is external impedance matching needed?
Yep. Good question, Les. No. Straight answer. All our filters in this portfolio are internally matched, let's say. To 50 ohms. So if you need something different than 50 ohms, then yeah, I guess you would need some external matching. But if you, I'm kind of joking. But yeah, 50 ohms, you know, maybe you know, a little tuning here and there is possible, but for the most, you know, 50 ohms isn't always exactly 50 ohms. It's 49.5 or something. So you may want to tune it even more, and that's possible, and we could help with that. We could help a lot with that, actually. We have some simulation tools. But yeah, there's no external required. That's on 2.4 and 5 and 6, by the way.
All right. Thank you so much, Cliff, for that last answer. So those are all the questions we have right now. Attendees, feel free to ask anything following today's webinar. You can always come back and ask any questions that you might have after this webinar is on demand. So at this point, Cliff, we're going to wrap things up. Any questions that may pop in the next minute or two, you can grab those, and we can always answer that person following today's webinar. So let's start to wrap things up. So I want to say a huge thank you to Cliff for being here with us today. Great presentation and for answering our attendees' questions. So Cliff, thank you so much.
You're welcome.
All right, and anyone that's asking any last-minute questions, feel free to do that, and we will get back to you following today's webinar. As I mentioned, we do have a link that will be coming out to you. You will be able to watch this webinar on demand for the next 90 days, so feel free to come back at any time to watch the presentation again. And as I mentioned a couple of times, there is going to be a survey that pops on your screen at the end of this webinar. So if you'd like to fill that out, your feedback is always important to us. And for anybody watching this webinar on demand, you're going to find that survey located along the bottom of your attendee console in the survey widget. And then just one last reminder about grabbing that PDF in the resource list on your way out today. So I want to say thank you, everybody, for taking time to attend this webinar event. Take care, and we will speak with all of you soon.